All right, I think we're ready. We're gonna do second part, frames and machines. Last time we actually did exam one. I'm still working on finalizing all the partial credit parts to that. So if you see some that look like they need partial credit but don't have it, it's probably because I haven't done it yet. But the time before that, we did a beginning part of frames and machines. And so I thought today what we would do is basically work a lot of examples for frames and machines. If you have a particular question about frames and machines, then go ahead and put that in the chat and I'll see if I can find an example for us to work that might cover that topic. Frames and machines are going to be the first topic on exam 2. The stuff that we did prior, so all the exam 1 things, some of those build into frames and machines and the torsion stuff. Some of the other content like the trusses, they don't really build into frames and machines, but you can't completely dump all of that knowledge because we are, for exam 3, going to go back and have a few problems from trusses, centroids, things. Actually, centroids will be a big part of this middle section of the course also. But trusses in particular, we will pick them back up for exam 3. So don't totally forget all that stuff. Keep it fresh. Maybe work one of the optional problems or something every now and then to practice on those. But we will pick those back up just for exam 3. And the project, there's a group project later in the quarter. It is trust based, so you will have some trust related topics there. But right now we're doing frames and machines, and we, in our first frames and machine talk, we had said that you cannot treat frames and machines the same as you treat trusses, particularly talking about method of joints and method of sections. You can't really use method of joints and method of sections on frames and machines. They have to be treated separately. And what we did is, we went in, and here's the work from last time. We did just this one, we just did this one frame, had a distributed load on it. That distributed load meant that it was not a truss because there was force applied directly to the member and not to just the joints. And so we took it apart, drew free body diagrams for each piece, and then worked on solving for these joint reactions for the frame pieces. And that's what we're going to do more of today. We're just going to use some problems. Let's see if I can find the ones I want. Over here in web work, we're going to use a couple of these. These are in the optional 2. So optional 2 are kind of the set of problems that are optional but go along with exam 2. And here's a frame. It has a distributed load across the entire top piece up here. The entire beam across the top has a distributed load on it. There's a point load, concentrated load over here on the side also. This point E, the supported E, that's modeling a roller or showing a roller. And then A is a pin. So why don't we copy this and take it over to our OneNote page and see if we can work on it. All right. So the first thing typically that you're going to do is decide if it's a frame or a machine. Because if it's a machine, you may want to go in and work on the taking the pieces apart before trying to solve external reactions. If it's a machine. If it's a frame, then you probably do want to find external reactions first. Maybe identify 2 force members if there are any, and then start taking it apart. It's not 100% you do it that way every time, but that's generally true. So this one I'm going to call a frame. It doesn't really have any mechanisms that look like the pieces move relative to the other pieces in this structure. And that means it's probably a frame. And it probably does mean that I need to find reactions at the pin and roller first. And maybe look for 2 force members. So to find 2 force members, what we want to do is we want to go in and look for any member that has only 2 pins connecting it. Now, sometimes the two force members will have a pin and another type of connection, maybe a slider or some other kind of connection. Those can still be two force members also. So typically it's two pins, but one of the pins could be some other type of connection. And so this one, we've got across the top, we've got member CDE. CD has two pins, but it's got this other thing, E, the roller at E, which is technically not a pin, but it's this other connection point to the little platform it's sitting on. So CDE has too many connection points, so it's not a two force member. ABC has three pins. There's the pin at A holding it to the ground, the pin at B holding the little diagonal piece, and the pin at C holding the top and vertical piece together. So those are not a two force member. BD has two pins, one at B, one at D. There is no force applied directly to the member. There are only forces, at B and at D, which that's okay. So member BD is a two force member. Now, if that will help us later on, we don't know yet, but sometimes you can't even solve for the complete set of values that you're looking for. Usually you're looking for the reactions at the pins. Sometimes you can't even find those if you don't identify the two force members. So member BD is a two force member. We could do that later, but a lot of times I like to look for the two force members up front. Sometimes they're connected to the external reactions, and that will help you figure out the reactions a little bit. Not all the time, but sometimes. All right. Now what I need to do is I need to go in and find the value for any of the external reactions I want. So this problem is asking me to find the stress, so sigma, in member BD, the tau at C, so that's the shear stress at C, so that means that pin at C, how much shear stress is on it, and the change in length, so how much is it stretching or compressing of member BD. So I'm going to end up needing to find information that tells me the forces at C, so CX and CY, and the force in member BD. Now that I know that member BD is a two force member, I do know the direction of that force. I just don't know the magnitude, and I don't really know if it's compression or tension. I could, guess which one it is, but I don't know that yet. So it looks like I could probably get away with either working on member ABC or member CDE. So in that case, I think I'll just do summation of moments about A in order to find the reaction at E, find EY. So let's do that. So I'm going to cheat a little bit, and I'm going to just kind of color this out instead of redrawing the whole thing. I'm just going to do that, erase it. I guess my color here I'm using is not quite the right color. It's a little bit gray, but that's okay. And then same thing down here. We're going to, it matches the background color there pretty well, just not the white color. All right, so we've got a free body, but we don't have any forces on it. So the reaction here was a roller. I'm going to call that EY. And then at A, there was a pin. I'm going to call that AX and AY. Okay, let's go ahead and label. I've got, WF, RST, UV, all these things that need to be labeled. So let's label those. W is 1600 newtons per meter. F, 2100 newtons. We've got all these dimensions on here. R is 330 millimeters. I'm going to write those as meters just because. So 0.33 meters. S, 0.34 meters. R, 410 millimeters, so 0.41 meters. U, 0.087 or 0.872 meters, and V is 0.41 meters. Okay. Now what I need to do is, if I want to work on member CDE, it's possible that I could just get this value for EY, take CDE by itself, and solve for that one without ever needing AX or AY. The problem's not specifically asking about AX and AY, so looks like I might be able to get away without worrying with that one. So let's try Summation of Forces. Or not forces. If I do forces in Y, I have EY and AY both unknown. So I would have two unknowns in the equation, couldn't solve for it. If I did forces in X, that has nothing to do with EY. I guess I could solve for AX. And so what I'm actually going to do is summation of moments about A. About A because AX and AY would not enter into the equation because their line of action goes through or intersects point A. So they're not creating a moment about point A. And that will leave me with only EY as an unknown value. So I'm going to say clockwise is positive just because I like that. Are R and T supposed to be switched? Oh, it's possible. Let's see. R is 3. Oh, you know what? I did do that backwards. Good. That would have created all kinds of problems I would have never found. So thank you. R is 0. Well, let's do it in blue like the others. 0.33 meters. T is the 0.41 meters. So I had those labeled backwards. Let's make sure I didn't do any others that way. S is 3040. U is 872. V is 410. Those look fine. But yeah, those were backwards. All right. Actually, it may not have mattered because of what I'm going to do in this case. Oh, it would have mattered because it would have changed the angle of BD, which would have been bad for us later on. All right. So let's go to moments about A for our entire free body diagram. AX and AY do not create moments about A. That's the same thing as trying to open a door by pushing on the hinge. You know, your line of action for your force you're applying to the door intersects the hinge, which does not make the door rotate. So F, though, does have a moment arm. So I've got 2100 newtons. And it has a moment. It's a horizontal force. And if it's horizontal, then I need the vertical distance between its line of action, the line of action of F, and point A, which looks like it is 0.75 meters. That's just S plus T. EY would rotate if it was actually allowed to rotate about point A, then EY would cause this frame to rotate counterclockwise, so it's going to be a negative. EY is a vertical force, so I need the horizontal distance between its line of action and point A. So that's going to be the 0.872 plus 0.41 is 1.282. And then I've got the distributed load across the top. So when you're doing moment equations for distributed load or even summation of force equations, it's usually best to go in and lump that load into a single point load. And the value for this point load would be 1600 newtons per meter times 1.282 meters would give me the lumped or concentrated value of the distributed load. So 2051.2 newtons. Let me make sure 1600 times 1.282 looks right. All right. And I would put this in the center of the span of the distributed load. Now I'm actually putting at the centroid. So if you think of the orangish, red, whatever colored distributed load, it's just a rectangle. And so the centroid for that is at its center. But we could have some of these where the distributed load is some other shape. You know, it's a triangle or a quarter circle or semicircle or all these different shapes. What you do once you calculate the value of the distributed load or the concentrated load, then you put that concentrated load at the centroid of this shape. So in this case, it's just in the middle of the span. So 1.282 divided by 2 is 0.641, and that would just be this distance. All right. Now I can go back to writing my moment equation. I needed that because instead of trying to write the moment equation as some sort of calculus function where this distributed load goes from C to E and creates a moment about A as as you go from C to E, it's simpler just to lump the thing into a concentrated force and take that concentrated force, 2051.2 newtons. That's a vertical force. All of the little distributed arrows are vertical, so the lumped arrow is also vertical. Multiply that times the moment arm from the concentrated version of the distributed load to point A, which I labeled as 0.641 meters, and decide if it's positive or negative. So it would go around clockwise around point A, so that I said clockwise is positive, so it'd be a positive. Now the only unknown in here is EY. So we should be able to solve for a value for EY. And it does come out positive. All these numbers are positive. When I move EY to the other side of the equal sign, it's positive. So that means that I drew the direction of EY's arrow correctly. All right, 2100 times 0.75 plus 2051.2 times 0.641 divided by 1.282, I get EY is 2,254.15 newtons. That seems reasonable to me. I don't have a reason to believe it should be some other number, but it is a little bit high because you would think it would be more or less half of the distributed load, except that force F over there is the way it's pushing on the frame causes the frame to want to rotate clockwise, which would send it crashing into that little shelf that I erased. And so that's why EY is greater than what it looks like it probably should be. So I'm okay with that being true. We'll find out soon enough. All right. At this point, you have a choice. You could go in and find AX and AY, which is, if you're unsure, maybe that's what you do just to keep working on the problem. In this case, we don't need that because of the specific things that this problem is asking for. We don't actually need to solve for AX and AY. We can go straight to disassembling our frame and looking at individual pieces of it. And so I would look at piece CDE. And I'm going to put the distributed load across it just because I want to remind myself that it's a distributed load and not a point load. And that doesn't really affect what we're doing here. But once we get into talking about whether or not these beams are deflecting, they're bending, and how much are they bending and what bending stress is in them, then it does make a difference if you treat a distributed load as a point load for flexural stress equations. So we're not there yet. So it's not gonna affect what we're doing today. We could have just drawn the lumped load. I'm gonna go ahead and draw the lumped load in. But in future work, it would affect it. All right. So I've got EY. Somehow I lost that arrow. It's redrawing really very strangely. All right. So this EY was 2,254.15 newtons. I've drew in the lumped load over here with the 2,051. I've got BD. I'm just going to draw it as an arrow, and it's just going to be force in BD. Since I know member BD is a two-force member, I do not have to write dx and dy just like it was an ordinary pin. So that saves me a unknown value. If I did not know that member BD was a two-force member, I could draw this free body diagram, but I'd have to draw dx and dy there because I don't know the direction of the resultant of them. But since it is a two-force member, I know that the direction of the resultant is on the line between point B and D. So on that line, I know that is the line of action. At C, I have member ABC pinned to CDE, and so I know that there are reactions there. I don't know their values, but CY and CX. So I know that there are some pin reactions that are holding member CDE to member ABC. Let's put our letters on here. So this is C, this is D, and there's E. Okay. We have some dimensions that we know also. We know that this dimension is the 0.872 meters, and this one is the 0.41. We know a little bit. Let's move this guy up to there. I know a little bit about this angle because I know it's rise and run. I did those backwards when I said them, but that's okay. The run is 0.872. The rise is 0.67 R plus S. And then we can get our hypotenuse, 0.67 squared plus 0.872 squared. Square root of that is 1. I'm just going to call it 1.1. It's actually 0.997, but that would round to 1.1, we'll say. Okay. And then I know the distance here. Wow, that's getting really cluttery. Let's find another place to put that. I'll put that in green, kind of in here. And it's the 641. Okay. Now, since I did draw member BD as the force in member BD at this angle, I only have 3 unknowns. If I didn't know it was a 2-force member, I would have 4 unknowns on this free body diagram, and I wouldn't be able to solve for all of them. Not without drawing more free body diagrams. But in this case, since I did identify it as a 2-force member, I only have 3 unknowns. So I should be able to solve for 3 unknowns because I have 3 equations to work with. So let's work with those equations a little bit. Get some more room here, if I can. There we go. I don't like writing over there. I'm going to move it. I'm going to move it over to here. Okay. All right. Let's do what we normally do and do summation of moments about the pin with the one with 2 unknowns, which is C, and that should give us a value for BD, which is most of what they're asking for, although they are asking for the shear stress at C, so we will need to find CX and CY also. So let's do moments, summation of moments about C, clockwise positive. They should equal 0 because we know this top piece is not rotating about point C. So I've got my 2051, I'm looking at the green arrow, 2051.2 newtons with a moment arm of 0.641 meters. I've got, let's skip BD for now and come back to it. I've got a negative EY, which we found to be 2254.15 newtons. It has a moment arm of, that number was 1.282, yeah, meters. BD is at an angle, so we're not using vector math type work here, so we can't just do a cross product. We need, what we're going to do is we're going to break this into a y component and an x component. The x component, its line of action goes through C, so I don't need to worry about that one. So I just need the y component, which would be BD times the y part of this, the y component of this, which would be 0.67 over 1.1. Or you could calculate the angle and do the sine or cosine depending on which angle you're dealing with. So the force is that is going around clockwise, so it is plus BD, the one we don't know, only the y component, oh, not 0 over 1.1, the hypotenuse. And this is where a lot of times I'll make a mistake because I get in the habit, I'm doing moment equations, and when you calculate a moment, you do a force times the distance, so you're multiplying two things together, and that's how you create the moment. Here, I will sometimes forget that this is not the calculation. This is just the force, but I have multiplied two things together. So don't do too many things just automatically, because you can easily skip over something. This BD times 0.67 over 1.1 is just the y component of the force. I still need to multiply it times 0.872 meters. Those should all add to 0. I'm going to have to do these a little bit at a time. So 2051.2 times 0.641. This is 1314.82 Newton meters minus 2254.15 times 1.282, 2889.82 Newton meters, plus BD times 0.67 times 0.872 divided by 1.1, 0.5311. That would be just meters, I believe, would be the units on that. BD is going to be in newtons. So therefore, and that is positive, this is negative. So I'll take the 2889.82, subtract 1314.82, so I get the difference in those two. That ends up being a negative 1575. I can move that negative to the other side, it becomes positive, and I get BD, well, 0.5311 meters times BD equals 1575 Newton meters. Therefore, the force in member BD equals 1575 divided by 0.5311, 2,965.54 newtons. It came out positive, so that means I've drawn the arrow the correct direction. Now you need to know which arrow did I draw. So I drew the arrow pointing away from the body, CDE. So when I draw the arrows pointing away, that's of a member, an internal member force, then that means that it is a tensile force. Even though it looks like that arrow is pushing on member BD, if I were to draw member BD, remember, I have to put the same line of action, but it has to have the same magnitude, BD, the 2900 number, but opposite direction. I drew at D that it goes down and to the left, so that means at the corresponding piece, it goes up and to the right. And then for this piece to be in equilibrium, this one would have to go down and to the left. And those arrows, when you draw those on member BD, it clearly is in tension. So you do have to try and work out, if member BD is in tension or compression. I don't know if this particular problem cares. It doesn't say anything about it, but it could. It could be that you would need to write a negative stress or a negative force if it were actually in compression. So what it really wants is the stress in member BD. We have the force there. Let's see what we have for cross-sectional area. Cross-sectional, or it has the rectangular. Remember, BD has a rectangular cross-section, 45 millimeters by 15.5 millimeters. All right, 45 by 15. I'll forget that. We'll try. So the stress in BD equals the force in BD divided by the cross-sectional area of BD. The force is a positive 2965.54 newtons. And the area, yes, I did forget it, 45 millimeters by 15 and a half. I wanted to do that. Now this will give me units of newtons per millimeter squared. And so I do have to kind of, is that megapascals or gigapascals, or do I want to convert the millimeters over to meters? You know, however you want to do it. If you do newtons per millimeter squared, that would be a megapascal. So I'm going to leave it this way, but the units that we're going to write will be megapascals. So 2965.54 divided by 45 times 15.5, I get 4.25 newtons per millimeter squared, which would be 4.25 megapascals if we did the conversion. So you would have to do 4.25 times, there are 1,000 millimeters in a meter. You have to do that twice, so that would end up multiplying times 10 to the 6th, and that would give you your megapascals. So let's see if that's even right. 4.25 probably is not right. It probably needs more decimals, but let's just see. Let's see what WebWorks says. I'm going to write it in. Actually, the units here are megapascals, so let's try the 4.25167 and see if we can get a green box. First, we got to log in. We did get a green box. All right, good. And we were off by, 10,000 or so of a megapascal. And we still got it right. All right. All right, so that gives us the part A. Another BD term is the delta, so the change in length. So let's do that. Now, it did tell us a material. Annealed invar. So I do not know the modulus of elasticity of annealed invar, so we're going to have to look that up. Let's see if I can find the... let's see if I can find... Oh, not that. Where's it at? It is in here. There it is, actually. Material properties. Oh, well, it's a download. All right. We need the metric units for this. Annealed invar down here in the bottom of the non-ferrous metal alloys has a modulus of elasticity 140. The units on that are gigapascals. So let's use that and figure out our change in length. So E 140 gigapascals. We want to know delta of BD, so the change in length. It should get longer because it is a tensile, remember? Tensile forces on it. And the change in length is the force in member BD times the original length of member BD divided by the modulus of elasticity of member BD and the cross-sectional area of BD. So we have the force is that 2,965.54 newtons. The length, I actually don't know. Oh, the length we do kind of know because we did we completed the triangle over here with the rise over run, so it's 1.1 meters is the length. I don't remember how much I rounded on that one. E is 140 giga, so that's times 10 to the 9th pascals. Area is this same thing, 45 millimeters times 1 meter per 1,000 millimeters times 15.5 millimeters. I'm going to run out of room. Times 1 over 1,000 meters per millimeter. Kind of ran out of room there. So let's see what we get for this. 45 divided by 1,000 times 15.5 divided by 1,000. It's going to give us a tiny number, but then we multiply it times 140 times 10 to the 9th. So we end up with a relatively large number in the denominator. Then we've got 2965.54 times 1.1. That's the numerator divided by our denominator. I get a small number. Now, the way I've done this is it comes out in meters. So 3.341 times 10 to the negative 5th meters. So I'm sure this wants us to put it in millimeters. Let's check. Yeah, it wants millimeters. So let's multiply times 1,000. So 0.0334, that's a 3 millimeters. And let's see if that's acceptable. 0.033 millimeters. Oh, we didn't put enough decimals. I have 3341. It's 3338. I bet if we put the others in there, 3341, we're probably fine then. Yes, we got it right. All right. Now let's do this last part. So the last thing it wanted us to do is the shearing stress. I'm reading right here, up here at the top. Shearing stress on a cross-section of pin C if it is loaded in single shear. So the single shear part means that the way that member CDE is connected to ABC would require the pin at C, the bolt or whatever it is, to only break at one cross section. So if we were to draw that, I don't know how well I can draw this, but let's look at it this way. So here is ABC. So there's ABC, kind of standing up vertically, and then CDE is out this way. So that's CDE. And that pin at C is right here, or bolt, or whatever you want to imagine it being. And for this to come apart, it only has to shear in a single place right there. The pin only has to shear in a single place. So that's single shear. It could be, that you have cases of double shear or things like that where that pin would have to shear more than one time for the parts to come apart. So what this controls is our calculation for shear stress, tau, equals V over A. It controls that area. How many areas have to shear in order for this to come apart? So single shear means one area has to shear. Double shear means that two areas would have to shear. But we don't know V yet. So we haven't solved for any of that. So V is going to be the resultant of CX and CY, those pin reactions at C, and we don't know either one of those. So let's try and solve those. I'm going to copy this thing and put it down here so that we can start over on it on finding CX and CY. We did find BD. It was in the correct orientation. That was 2965.54. So let's put it in there. I'm going to get rid of that. All right, so BD is 2965.54 newtons. Now CX and CY are pretty straightforward. Let's do summation. I'd like some more room there. Summation of forces in the y direction equals 0. We have CY minus the entire distributed load lumped into that 1 point load, which is 2051.2 newtons, minus the y component of BD because it is pointing down. So minus BD, which is the 2965.54 newtons, but only the y component. So times 0.67 over 1.1. I'm going to have to move this over a little bit, aren't I? There we go. Plus 2254.15 newtons from EY. So the only unknown is CY. So we should be able to solve for it. Let's see. 2051.2 minus 2965.54 times 0.67 over 1.1 plus 2254.15. So this one you do have to do a good job. Oh, you know what? I didn't put, that's a negative 20. So I need to put a negative in there. Let's see. Where's insert on this thing? Well, let's just, I don't see where insert is. Let's start over. Negative 2051.2 minus 2965.54 times, I want to make sure it does the order of operations correct here. 0.67 divided by 1.1 plus 2254.15. All right, now I've got negative, minus, and plus. I think that all works out right. So I end up with CY. When I move CY to the other side, it becomes negative also. Negative CY equals negative 1603.33. And I could have looked at this diagram. Since I knew that BD is in the correct orientation, I could have looked at it and told you that's, well, I'm thinking of CX, not CY. CY, I would have assumed that it's drawn correctly, but it could be that it would have to pull down or do some other thing. But it does look like it is drawn correctly. All right. So that actually, those two negatives cancel out, and CY is 1603.33 newtons. And then we would do summation of forces in X. This is the one I was actually thinking about. X is pretty obvious that it's drawn correctly because the only other force in the X direction is the X component of BD. So we've got the summation of forces in X equals 0, CX minus, because BD points to the left, BD, which is 2965.54 newtons, but I only want the X component, so 0.872 over 1.1. So that, multiplying by that, gets me the X component. You don't have to do the rise and run and hypotenuse. You can, if you're more comfortable doing, calculating out the angle and doing cosine inside of that angle, then that's totally fine. This, if you can get comfortable using this, it might speed things up slightly, because you don't have to go calculate the angle, figure out what it is, just to take the cosine of that angle when this is the cosine or the sine of the angle. In this case, it depends on what angle you're talking about. All right, so if I do this, then CX is equal to 2965.54 times 0.872 divided by 1.1, 2350.86 newtons. So there are my X and Y components for the resultant at C. So C, the actual force that goes into this shear stress equation, is equal to V. So it is the shear force, and it equals the square root of CX squared plus CY squared. So that's the square root of 1603.33 newtons squared plus 2350. It looks like I wrote CX and CY, but then I wrote them in the other order. So let's clean that up a little bit. There we go. 2350.86 newtons squared. So let's see what that is. Square that number plus 1603.33 squared. Square root of those is 2845.56 newtons. So this is the resultant of those two, well, these two forces acting at C. Don't get confused that there is, this arrow from the distributed load also pointing at C. We don't really take distributed loads and look at just a little piece of them, at least not for this. The reactions at C take into account the entire distributed load. They do that right here, right? So CY, part of calculating CY is taking into account the distributed load. So let's go back to, oh wait, we need to know the size of this pin. Let's see. All pins have a diameter of 12 millimeters. So there we go. So tau at C equals the shear force at C divided by the area of C. The shear force at C is that resultant CX squared plus CY squared. Take the square root. So 2,845.56 newtons. The area of C is pi. It said that they all had 12 millimeter diameters. Pi d squared over 4. This will give me newtons per millimeter squared again. And so this will actually give me megapascals when I calculate it. So 2845.56 divided by, actually I'm going to do it the other way. Let's do 12 squared times pi divided by 4. And then 2845.56 divided by that answer. Oh, that's actually kind of high. 25.16 newtons per millimeter squared, which is 25.16 megapascals. So it's not terribly high, but let's look at material properties again. I think they're still up. Here they are. So remember, we're talking about a shear stress, so that means we need to compare it to a shear strength. It doesn't, I don't think it says what these pins are made of. There's the right number, 25.15, which is what we have, more or less. Annealed invar for the members, but not necessarily for the pins. So let's just say the pins are some kind of steel. So here's that generic structural steel. There is no number over here for the shear stress, so that means, or shear strength. So that means we take half, our model is anyway, that we're taking half of the tensile. So 125 would be our shear strength. And we have 25 as our shear stress. So we still have a factor of safety of 5, but it's closer than it might appear. So we're still are plenty safe though. And if we plug that in, we just saw that it was the right number. 25.15 is the number that WebWork actually had. So this problem, it's pretty straightforward on the frames and machine side of things. It does include a couple of things. You've got the distributed load. You've got the two-force member defined. If you don't find that two-force member, then this ends up being a simultaneous equation solver thing, because you have to write the free body diagram for ABC and CDE to get enough values to solve for everything. Even then, you would have 1, 2, 3, 4, 5. Yeah, you could do it then. You'd have 6 unknowns because you'd have dx and dy, and you'd have bx and by that you don't know. And you'd have to write the entire set of equations, 3 each, for member CDE and for ABC, and solve this thing simultaneously. So it could be done, but it would be much more difficult. So when you find the two-force member, you eliminate a bunch of your unknown values because you don't have to write dx and dy and bx and by. You just write the force in BD at both of those places. In fact, if we didn't even draw member ABC. So that's a key part to it. But it's still one of the simpler frames and machines. So this would be kind of that mid-range level problem. It does get a little bit more involved because this particular one is asking for stress and change in length. So that makes it a little bit more than just a regular average problem. If all you were trying to do is find the force in member BD, like here, then this would definitely be one of the average level problems. All right. Now, here's another thing. That took us 50 minutes to talk through. Now, we spent a little bit of time up front talking about the exam, but still 40 minutes minimum to talk through. So you can start to see where that's a problem on an exam, because you can't spend 40 minutes working through one of these things. Now, you don't have to sit there and talk through every little detail. You can work it much quicker, but I did notice on exam 1 that people were running out of time towards the end. So there is a time constraint, and usually what I do is I adjust, if there's a problem that just everybody didn't even get to or whatever, then I usually adjust the grades to account for that. But you do have to figure out spend a few seconds looking at the thing. What is your approach going to be? Are you going to be able to solve this without doing simultaneous equations? If so, what's the way to do that? So if you spend a few 10 seconds, 15 seconds looking at it beforehand, deciding what you need to do, kind of map out the procedure, you won't end up in those situations where you got to solve a 6x6 set of simultaneous equations in order to get to the end of the thing. So it is worth it to spend those few seconds to try and figure out, oh, I really only need the value for EY, which has disappeared again. I think it's because all this color it just hides behind it. That's fine. We know it's there. There we go. So it spends, you don't have to worry about finding AX and AY. You've identified the two force members, so there are things you can do to make this much simpler to solve. All right. I think we do have time for another one. Let me look through our web work and see if I can find a good one that introduces some new things. So let's see. This one kind of has some new things, has some two force members and a cable, so that's interesting. Let's see what else we have to choose from. This one is one where you don't have to find the external reactions first. So that's this was a good one to look at and figure out, well, I don't actually need to find the reactions at all. This one has a slider. This one might be worth doing. It has a slider right here. Or slot. Maybe it's not a slider, but more like a slot. So just in case we don't work on this one, the slot has reactions that are perpendicular to the slot. So that's it. It's just like a roller. And so you know that the reaction is perpendicular to the slot itself. What else? That's just a beam. So that might be all of our frames that we have to choose from. I think this may be the one that we do because it has some trickiness to it. I may even have to think about what's going on there. But I think I see how we can go about doing it. All right. So this is a interesting one. Okay. Let's put it over here. And ask for a whole bunch of stuff. I don't know if we'll solve all of that, but let's just see what happens to this thing and how we can make it solvable. So 3 bars are connected with frictionless pins, so that's good. All of the pins in this course are frictionless. Frame is loaded with the force of 715 pounds. So this is 715 pounds. The dimensions on the figure are A is 6.1. These are feet. B, 6.2. C is 6.2. And D is 6.1. So it's setting up some symmetry there. That's good. E is 11 feet. Determine the magnitude of, and then a whole bunch of things, 6 different things. Enter all answers as positive, so we don't have to worry if it's up or down. And that's typically true on the joint reactions because they are both. If I look at member BDF and think about the reactions at D, they're one direction. But those same reactions on CDE are the opposite. So a lot of times with these frames of machines, you're just looking for the magnitude of the X and Y components at any given pin. So that's okay. So one thing I noticed, first of all, it's still attached to the ground, so let's do our same thing where we're going to, erase that. Those are both pins, though. So EY and EX, AY, AX. So I have 4 unknowns as external reactions. So anytime you have 4 unknowns as an external reaction, that means that there's some other thing, for this course anyway, that means there's some other thing going on because there are too many unknowns to solve for as just the external reactions, because you can only solve for 3. You have the force equation in y, in x, z does not help us here, and then we have a moment equation. So we have those 3 equations to work with and 4 unknowns, so we know that there's something else going on here. And what it is member BDF. So this is one where you could find AY and EY. Maybe that'll be useful later on. So we could find those, but we couldn't find AX and EX. All we know is that they're equal to each other, but they could be 0. They could be opposite values in the same magnitude, opposite direction, same magnitude. So I don't know. I don't know enough about them to be able to solve for those. I could find AY and EY. If I did moments about A, then that would give me a value for EY. If I did moments about E, or then at that point I could do forces in Y and get a value for AY. I'm not going to do that yet. We may need to do that later, but I'm not going to do it yet. So remember BDF. So I said when things are machines, a lot of times you have to start by taking them apart instead of solving reactions, but sometimes, this is a frame, sometimes you have to do that with a frame too. And so BDF at D, that's a pin. There are no 2 force members in here. You know, everything either has 3 connection points or 2 and a force applied to it separate. So no 2 force members. So at D, I just have regular pinned connection, which would give me dx and dy. I've got that 715 pounds. And then the key to this one is the pin at B. And the key is that it is on a slot or in a slot. And I know, since it's frictionless, that's the reason that they gave me this frictionless clue up here on this one. Since it's frictionless, that the reaction is perpendicular to the slot. So I don't know which way it goes, but I know that it is perpendicular, so the force at B is not Bx and By. It is the force at B, and it is perpendicular to the slot. The slot, if you look over here, the slot has a rise of 2 and a run of 1. So perpendicular to that would be and it looks like I kind of didn't draw it very well, but a rise of 1 and a run of 2. And then hypotenuse of whatever that is. Let's see. My calculator has a low battery. This is might be a problem. I don't remember the last time I put batteries in here. Hopefully it'll hold out. 2.236. Okay, that's the hypotenuse for this little triangle here. And clearly it's not drawn to scale because the rise I drew is 1 and the run is 2, but they're almost opposite the way I drew them. All right. Now, since I know how to deal with the slot, then I don't have 4 unknowns on here. I have 3 unknowns. So I can put some dimensions on here. This would be from B to D is 12.4 feet. From D to the 715 pounds is 11 feet. And I can do summation of forces in X or Y, but those have too many unknowns, so I need to do a moment first. So I'm going to do moments about, let's do moments about B. That seems good. A lot of times I do the moments about the place that has 2 unknowns, but in this case, since B and D are on the same line, they're both horizontal with each other, then doing moments about B will also eliminate 2 unknowns. It'll eliminate force at B, and it will eliminate dx. So I'll be solving for dy. So I've got dy negative, the way I drew it, dy times the 12.4 plus 715 times the 23.4. Whoops, 23.4. So therefore, dy equals, and it turns out that it's positive, So I did draw dy the right way. Let's see, 715 times 23.4 divided by 12.4, 1349.27. These are pounds. Okay, now I've got a value for dy. Are they even asking for that? They are asking for part B here, the horizontal and vertical components of force in pin D. So I've got the vertical one. Now, if I do summation of forces in the y direction, I'll get the value for FB. So I've got FB times only the y component, so 1 over 2.236 plus dy minus 715 pounds equals 0. And I do have a value to plug in for dy. So therefore, FB equals, let's see, I've got 1349 minus 715. I'll move that to the other side of the equal sign. It becomes negative. So FB is actually a negative value. I drew it the wrong way. So the 634 divided by the coefficient with FB, which is 1 over 2.236. So I get a negative 1418.237 pounds. So all that means is that I drew the arrow for FB the wrong way. This particular problem does say that enter all the answers as positive values anyway, so that doesn't matter for putting the answer in, but I do need to keep track of that for summing forces in X and Y, because the way I drew the arrow is opposite what it's supposed to be. So let's do summation of forces in X. And we have, I'm going to write this according to the free body diagram. So negative FB, the X component is 2 over 2.236 plus dx equals 0. But then I'm going to plug in negative 1418 for here. So I'm going to have the double negatives. So negative FB, so negative 1418.237 times 2 over 2.236. I'm going to move dx to the other side, equals negative dx. So I've got 3 negative signs here, so it ends up that dx is indeed negative. I drew it the wrong way. And it equals times 2 divided by 2.236, 12, negative 1268.548 pounds. And the negative again means I moved it the wrong direction. I drew dx the wrong direction. Let's see if we can get to check on any of these if they're right. How do they want these put in here? So dx was the 1268.548. dy I've forgotten. dy is 1349.27. 1349.27. We didn't do, oh wait, we did do RB, didn't we? Oh, we called it FB. 1418.237. 237, I think. And we haven't done any of these others. Let's see if it's going to give us any credit for these. Yeah, we got them all right. Good job. All right. Look at the rest of this thing. At this point, what I would do is, now that I have values for B and D, let's draw one of the other free body diagrams and see what happens. So let's draw CDE. All right, so at E, I didn't solve for any of those, so I just still have the EX and EY. At D, I have, all right, this is where you could easily get confused. Let's do C first. C, I'm just going to do CX and CY. Now let's deal with D. So I have a value for DY that I've already created a direction on this free body diagram, dy and dx, as going up and to the right. And so on this one, the matching reactions should be down and to the left, except that I solved for them. Dy was correct. It had a positive sign, so that meant that I drew that arrow right. So this dy is correct, but dx has that negative sign, which means I drew it the wrong way. So I'm going to put dy's value in here as 1349.27 pounds. And then dx, I'm actually going to redraw the arrow. You have two choices here. You can redraw it the right way, or you can keep track of the negative sign. And it's kind of a personal preference on which way is better, because both of them can get you kind of mixed up when you're looking at these. Sometimes it's actually better to keep the arrows consistent throughout your whole problem and just deal with the negative signs. But in this case, I'm going to do it the other way just because I am going to. But it's equally as valid to keep the arrow pointing to the left on this piece, showing that it matches, what we started with, as in an equal and opposite direction, and just keep that negative sign on there. So it's going to be which way you like to deal with that. So looking at this piece, CDE, it has 4 unknowns, CX, CY, EX, and EY, so I can't solve for all of those. So at this point, I choose, do I draw, remember ABC, create another set of 3 equations and do a 6x6 matrix? Or do I figure out a way to get EY? Probably what I would do, and since this particular problem is asking you to do everything, it wants you to know, every member force, and it wants every little piece. Probably what I would have done in that case, to begin with, is take the entire truss here. Let's move, or not truss, frame. Let's move this guy out of the way. Oh, I left one little line of something. I don't even know what it went to. Oh, it's the 1. Oh, it's going to be hard to grab, isn't it? All right, just erase it and draw a new one. It's that 1. So what I would probably do is go to the whole free body diagram. Summation of moments about A equals 0. We'll do clockwise positive. AX, EX do not create moments about A. AY does not create a moment about A. EY does. So minus EY times all of these 6.2s and stuff added together. 6.1 plus 6.2 times 2, 24.6. Those are feet. And then the 750 pounds, so plus 715 pounds, plus 6.1 plus 6.2 plus 6.2 plus 11, 29.5. And solve for EY this way. So therefore EY equals 715 times that 29.5 divided by 24.6, 857.42 pounds. And it does come out positive. And once I know that, then instead of having EY over here, I have 857.42. And I've got the 3 unknowns, CX, CY, and EX. And then I would do moments about C, probably. Clockwise, positive. I've got the D X value creating a counterclockwise moment, so minus 1268.548 pounds. That moment arm is not given to us, so we have to figure it out. It's this distance, here. And I don't have that distance, at least not labeled directly. I've got triangles I can work on though. So I've got all of this as a triangle, and I have its rise and run, so I have its slope, and I have the base of it. So I can figure out by similar triangles, you know, this guy, I can figure out the height of that similar triangle in there. So, oh, I don't have the height at all of it though, do I? Okay, so we got to do something different. Do I have any height values at all? I just have the slope. Well, I can calculate the height of the bigger triangle. So the base is 6.2 plus 6.1. So that the base is 12.3 across from the center of one of these, the whole frame to one end or the other, since it's symmetric. And it has a ratio of 1 to 2 base to height. So that means its height is twice this. So the total height, 24.6 feet. And then I can do the similar triangles to get the height of just this section. So similar triangles would say, what would it say? Let's see. I've got a running out of room to write things in. It's getting kind of crowded. Let's see. Oh, we can write it right here because we were working on that equation. Let's move that down. All right, so I've got this triangle, which has a base of 12.3 and a height of 24.6, and it's similar to this triangle, which has a base of 6.2 and a height of what I want to know. So let's see. $12.4. Okay. That should be right. Well, yeah, I guess it's still got the same slope. I didn't have to make it very complicated, did I? It's still got the 1 to 2 slope, so it's still twice as tall as the base. All right, so now we've got that height. So that is right here, 12.4 feet. Looking at our picture here, the 1349.27 creates a positive. It has that's that vertical force. It has a horizontal moment arm of 6.2 feet. And EX is, the way I drew it, is going around in a counterclockwise, so negative. It has a moment arm of that 24.6, the height of the entire frame. We might need to move this over a little bit more. $857 also goes around counterclockwise, so minus 857.42. Its base is the 12.3, or not the base of the triangle, but its moment arm, I meant. All of those have to add to 0. The only unknown in there is EX, so we should be able to keep track of all of this and solve for it. Let's see. 1268.548 times 12.4. So this first number is negative 15,729. Well, let's just call it 730. That would be foot-pounds. Plus 1349.27 times 6.2, 8,365.474 foot-pounds minus EX times 24.6 feet minus 857.42 times 12.3, 10,546.27 foot-pounds. equals 0. We'll move EX to the other side so it becomes positive. And let's add up all these things. So I've got negative 15,730 plus 8365.474 minus 10,546.27. So the left side is negative 17,910.77 foot-pounds. And the right side, I move EX over, is equals EX times 24.6 feet. Therefore, EX, I drew the wrong way. Divide by 24.6, 728.08 pounds. Let's see if that is correct. Oh, I don't know where EX is. EX is right there. 728.08. And again, we're putting this in as positive because of we could have drawn the arrows any direction, and hey, we got it right. So you can see how this particular problem is going to be very lengthy. I think we've got the idea of what you would do. Next, you would do forces in X and Y for this same free body diagram and get values for CX and CY. Once you do that, you're almost done. At that point, you draw A, B, C, and you know CX, CY. Actually, you don't even need to draw that. You can go back to the entire frame as a whole and solve for forces in X equals to 0, and the only two things are AX and EX. So AX and EX have the same value. Opposite directions, but this particular problem is not asking for directions. So we would have for AX, we would have the same 728. And it should like that. And it does. So this one, you know, obviously not going to be a test question to answer all of these, but this problem style is a good one for the harder frames of machines because it looks like it's this really long drawn out thing. If I'm asking for maybe the force at member B, we got that early on, way up here. We could have gotten it first, well, after, actually no, we could have gotten it the very first thing. We could have drawn this free body diagram, done moments about D, and found the force at B, and been done with the whole problem. But if you don't know that the slot creates a perpendicular reaction when it's frictionless, which ours are, then this problem gets to be really complicated because you got to go through and do all these, work on one piece for a while to get enough answers to move to another piece to, you know, solve something on there, and it gets really complicated. So that's what would make it'd be an easier advanced problem on an exam, only because it does have a easy solution. You could write just this one line, draw this free body diagram, and write this equation. Well, not that one. Write a moment equation, but moments about D instead of about B, and you would get a value for the force at B. And so it requires one of those where you look at it for a few seconds, figure out what you're going to do to solve for the thing that you need, and realizing on an exam you're not going to be solving for 6 different things, each of which has 2 components. You're not going to be doing all that on an exam, at least not on this exam. Maybe some other day. I think that, I mean, we have some time left, but I think this probably gets us far enough along. We did some review of some stress and axial deformation. We solved plenty of little free body diagrams for frames. We didn't technically do a machine. The only difference is that for a machine, most of the time you start by taking it apart and looking at individual pieces of the machine. I think this is a good stopping point for now. We might do another frame and machine next time, particularly if I get a lot of questions about anyone from homework. Homework 9, I believe, is the one that's open right now, plus the challenging and optional 2s. I think that's the one that's open and has some frame problems. So start working on those so that if you have questions, we can go ahead and answer the frame questions before we've already moved on to beams. All right. I will see y'all on Wednesday. And I think, let me know if you have questions about any of these frames and machines stuff. A lot of times it's the one that's of the content we cover the most difficult to get around, figure out what's going on with it, because it does require a lot of bookkeeping, arrows going in different directions. What if they're negative? A lot of little details you got to keep track of. So start working on those so we can get answers to any of your questions. I will see y'all on Wednesday.